So our next speaker is Estrela from JPL. She's going to tell us about more exoplanet atmospheric escape.
Thank you.
Okay, so the time is there. Yeah.
Okay.
Take it away.
All right, thank you. All right. Hello, everyone. As introduced, my name is Estrela. I'm a research scientist at NASA JPL. Can you hear me if I'm far away? Okay. Yeah, and today I'm going to talk about the fate of rocky exoplanets' atmospheres under the influence of the host star. We are entering in an era of the exoplanets' atmospheres, and that's exactly what the Astro-Decade 2020 is telling us. We are moving in the 2020s and beyond into characterization of atmospheres. We have the front coming with transits, with James Webb, we had Hubble, and in the near future, we're going to have also direct image. Josh Pepp is going to tell us about HWO. We're also going to have Rob Zelen this afternoon telling us about Roman. But on the transit front, we had a lot of initial efforts. Our pioneer, HST, Hubble, had tried to detect atmospheres in planets that are smaller than 1.8 Earth radii. I really like this summary made by Natasha Battaglia in the Sagan workshop at 2023, where we can see that, let me try to point this thing. Yeah. Where we can see that most of the observations with Hubble resulted in non-detection, which is highlighted in gray, but there were two tentative detections, one of H10 and GJ1132, and another one of water in HLS 1140b. And now we are moving, and we have a new space telescope, James Webb, which is doing amazing science. We have seen a lot of them in this workshop, in this conference, but for the small planets, it's still a complicated scenario where we're seeing some inconclusive results. And this is a TRAPPIST-1c, where we cannot tell if this measurement with James Webb resulted in it's a thin atmosphere or if it's a no atmosphere at all. The observation is consistent with both scenarios. So the observations are doing a great job in trying to answer if rocky planets have an atmosphere or not. But if we want to answer when do rock planets retain atmospheres and why, we also need to understand the factors that's going to influence in the evolution of the atmospheres of these planets. Especially also if you want to give context to these observations that we are doing nowadays with Hubble and with James Webb. And there are many factors that can influence the planetary evolution. So the planet that we are expecting to observe today, it can be a product of life, magnetic field, geophysical process, but there is a very particular one, which is the influence that comes from the host star, especially because stars, they change through time. And when the stars are younger, they are going to be way more active, they have faster rotation, and the X-ray luminosity that you see for a young star, this is for the solar-type stars, is much higher as the luminosity of the UV also is much higher, and as the star gets older, this X-ray luminosity is going to decay. So because X-rays and XUV in general can be very high, especially when the star is more active, this is very important because it can drive atmospheric escape. So we can have atmospheric erosion of the rocky planets' atmospheres. And we heard about that a lot in this conference, where XUV can give enough energy to ionize the hydrogen atom in the upper atmosphere of the planet, leading to the escape of these atmospheres. And that has been invoked to explain the valley that we see in the distribution of the small planets. So planets that originally were sub-Neptunes, they were more puffy, they have higher radii, they likely have a hydrogen in the atmosphere. These atmospheres were eroded by photoevaporation and they transitioned to become rocky planets. So basically, they jumped the gap. Of course, there are also other processes that have been invoked, like copper mass loss, to explain that valley as well. So one of the line of my research has been to look also into the XUV, which can drive the erosion process, and it can explain this transition from sub-Neptunes to rocky planets, in conjunction with also the planetary properties, like the amount of solation planets receive and their density. Density is especially a very important parameter of the planet because with density, you can tell if planet if the planet has a lower density, for example, we can expect that this planet still have an envelope, a hydrogen-helium envelope, which is the case of the sub-Neptunes that you see here in green. This planet have very low density. As we increase the density, you can see this cluster of planets here, which are consistent with this brown line, this brown cube, which is a Earth-like scenario, Earth-like composition, rocky composition. But what we can also notice in the rock composition is that there is a cluster of them that have very high insolation, which are the blue ones indicated in this plot, and there are some of them that are lower insulated, which is the red ones. If you look in the XUV at 100 million years, when the star is way more active, for the blue cluster, which is high insulated, we also notice that these planets also receive way more X-rays irradiation than the planets that are red or green. So that tells us that these planets, the blue cluster is likely to be planets that originally were sub-Neptunes. They received a lot of XUV, and they got the atmosphere eroded and became rocky planets. But now, if we want to look specifically for it's very important to look also specifically for the habitable zone planets, especially those that are orbiting M dwarfs, because these planets are going to be much closer to the host star than a planet in the habitable zone of a solar-type star. So for example, a planet that's in the habitable zone of M dwarfs can receive 400 times more X-ray radiation than a planet that's in the habitable zone of a solar-type star. So thinking about this problem, one of my students, Ashini Modet, she tried to answer this question. Do planets in the habitable zone of M dwarfs lose their primordial atmosphere? When I say primordial, I mean a hydrogen-helium atmosphere. So to answer this question, what Ashini did, and she was just a high school student, which is crazy, she calculated the amount of the accumulated mass loss that a planet would have throughout their lifetime. This is an example for TRAPPIST-1e, but she did that for 34 habitable zone planets. And she used two erosion processes. One's photoevaporation, XUV-driven, the other one stellar wind, a 1D stellar wind model. And if this erosion was above this red line, the planet would lose their primordial atmosphere. And the red line is an estimation of the amount of primordial atmosphere the planet could have accreted. So by doing that for the population of 34 planets, what she found is that with the 1D stellar wind model, planets would not lose much, but with the energy-limited photoevaporation model, especially planets that are below 0.1 AU, so planets that are in the conservative habitable zone, these planets will lose 100% of a hydrogen-helium atmosphere, including the TRAPPIST-1, all the TRAPPIST-1 planets. But that's not a very pessimistic scenario because atmospheres can be replenished. So planets can transition from primordial to secondary atmospheres. There is outgassing through volcanism, especially in the case of M-dwarf planets. These planets could be tidal locked, and the tidal heating could keep the mantle hot enough that gases that are originally trapped in the interior of the planet that are in the mantle, they can go and they can be released to the atmosphere. So that's an example here of outgassing of hydrogen. And we're seeing some cases of potential detection of secondary atmospheres with James Webb. This is a good example that came out recently by colleagues from JPL, Aaron Bellow, where there is a potential volcanic SO2-dominated atmosphere in the sub-Earth L9859b. So when we're talking about habitable zone planets, it's very important to understand if these planets have an atmosphere, retain atmospheres, but we also need to understand other properties of these planets in preparation for missions like Habitable Worlds Observatory. Habitable Worlds, it's going to be a large UV optical infrared space telescope, and it aims to identify and directly image at least 25 potentially habitable planets and search for chemistry of life. So because of missions like that are coming up in the future, we want to know which planets would be suitable for follow-up observations. Do these planets retain atmospheres? If they do, are they habitable? An atmosphere, we know that's crucial for habitability. And could these planets have false positive biosignatures? So thinking about this other problematic, it's very important to understand another influence of the star that comes from the FUV and the NUV irradiance that can have a very important impact on origins of life, but also can drive photochemistry. So in the impact of life, NUV can trigger parabiotic chemistry. It can give enough energy to trigger the chemistry of life. But for MDOFs, that might be tricky because their NUV is smaller than the NUV of a solar type star. So one of my students, Victor Sumida, who is here today right there and is presenting a poster, tried to see if by increasing the NUV of an MDOF, TOI 700, increasing the FUV received by a planet orbiting this MDOF, TOI 700, if we would get enough NUV in the surface of this planet that life could be, prabiotic chemistry could be triggered. And he found that if the planet had an arcane atmosphere and increased FUV by 10, yes, this planet would be inside of the abiogenesis zone. So the planet would receive enough NUV for prabiotic chemistry. And the other side, we also need to look photochemistry because of the potential false positive biosignatures. So Victor also in the same work, he also analyzed the photochemistry, increasing the FUV or with the quiescent star FUV. And what he noticed is, again, for the arcane atmosphere, in the low FUV, we are going to have a lot of accumulation of aerosols in the atmosphere. But when you increase the FUV, these aerosols are going to be break down. Actually, you're going to break down methane and every molecule that produces aerosols. So we end up with more CO2 and methane signatures in your spectra here. So I would like to finish my talk with a little bit of advertisement. There is the Habitable Worlds Observatory Science Meeting coming up in July, and we are accepting abstracts. The deadline just got extended to February 21, and we're also looking for not only exoplanet science, but all other kind of science. So please submit your work. And I'm going to leave with the key points because I'm out of time. Thank you.
Thank you very much. Questions? Questions? I'll ask one. Oh, there's one from Ward. Yeah.
Okay.
Great talk. I wanted to ask, when you're talking about raising the FUV by a factor of 10, did you look at some of the physical processes that could potentially achieve that level, such as flares or just increased quiescent emission?
Yeah, Victor actually looked into how much flares would increase. That's how he came up with the 10 times factor. But you can get more details with him after this talk.
Exciting. Thank you.
Yeah.
Okay, I'll ask one. Can you go back to the slide where you showed a plot of percentage mass lost? I think when you started talking about... Yes,
this one, right?
Yeah. So, and is this for a planet in...
That one?
in the habitable zone?
Yeah, these ones were, habitable zone planets.
So you have an accumulated mass loss of 10 Earth masses. Is that right? Am I reading this right?
Yeah, yes.
This seems like a lot.
Well, because that was accumulated back in time. So we started as the planet is today, and we were going back in time.
Okay.
Yes, and with photoevaporation, that was really a lot of, but I mean, there are a lot of uncertainties in the photoevaporation model, right? Okay. So there are uncertainties in the XUV, there are uncertainties in the coefficient of efficiency, so that was, we were also very surprised with the photoevaporation model.
Yes, we have a question there.
Thank you. That was a great talk. I wanted to know if there are any estimates on the rate of outgassing that is going on, like the planet is losing through the atmosphere due to NUV or XUV?
Sorry, I couldn't hear very well.
Yeah, I wanted to know if there are any estimation of the rates of outgassing, which are like, and stepping off the atmosphere due to XUV or NUV.
Oh, yeah. I don't have an answer for your question. I did not look into outgassing with XUV driven by any other process. So, no, I don't. I think it's a very interesting, it would be very interesting the next step for the for the field to look into this escape, how much is escaped, how much is being replenished. That's why I brought this topic, but I have not done research on that specifically yet.
Okay, we have time for one more quick one. Can the next speaker come down?
It was a really nice talk. For the study of TOI 700 where you increase the FUV flux, so in reality, when you increase the flux, the spectrum of the emission actually really changes, right? Did you do that, or did you leave the spectrum of the flux basically the same, right? So if you increase the flux, you'd expect actually a lot more high level energy as well, and that might change the results.
Yeah, that's a question for Victor. Because, yeah, I know that he increased it, but I don't increase the decreasing flux, but I don't really have an answer. Do you have an answer, Victor? Yeah. Okay. Yes.
Okay, let's thank Jose again.
Thank you.
Can you grab the microphone?